Okay, our next talk will be given by Malena, and the title of the talk is an LPLP variable projection method for large-scale separable nonlinear inverse problem.
Thank you. And I think that instead of having the whole screen, I think I will stay like this. You can see it, right?
Okay.
All right, so yes, I'm going to present this work, joint work with Mirieta Pasha. So let me, let's see if it moves. Let me start with the land acknowledgement. So I acknowledge that I work and live on the ancestral territories of indigenous peoples, including the Hohokam, Akimel, Odam, and Odam Jiwet Indian communities, whose care and keeping of these lands allow me and my family to be here today. I further acknowledge that Arizona, where I live, is home to 22 tribal nations that comprise 27% of Arizona's total land base. I recognize the sovereignty of these nations, and as a professor, I seek to foster a teaching environment of success and growth for Native American students. So I want to start motivating this work, looking at this X-ray radiographic imaging system. Here you can see already, let me just clarify two things in Spanish. Voy a poner some slides en español. So, así que la gente puede seguirme un poco mejor. All right, I was just clarifying that there will be some Spanish words. I try to, there is not many here, but I try to have the slides in Spanish. All right, so yes, so let's consider this imaging system. This is a very high, so you cannot put a person here. It will disappear instantly. So you shoot an object with a very high energy X-rays. And then to actually see what is happening, there is what is called a scintillator. And that basically makes things visible. And then with a camera, you can capture what is happening here in the scintillator. Now, this scintillator actually is going to produce some blur, and that is going to be basically the focus of this presentation. How can we improve or restore images, in particular enhance the edges that were lost in this blurring process? So here there is an example of an object and the cross section. So if you look at the cross section, this is what you see here. And you can see that instead of having a very clear step, you have these blurry steps. And I'll talk more about this. But I want to motivate all the work with this application. All right, so similar as Mirieta presentation, let me start by formulating the mathematical problem of this blur process. So suppose that you have an image, and then this point spread function or the matrix A will say what happens, what is this blurring process that happens to the image. By the way, here the notation is that we are really vectorizing the image. So here X is a vector. Even though this is really the PSF, how you deform a pixel with the information of the pixels around, this can be translated into a matrix. Okay, so here we are assuming that this blurring process is a linear process. Of course, we have noise, and then after this whole process, this is what we have. This B is where we have the data. So let me summarize again, but in principle, we have an image of something, an object, and then it was blurred, and then on top of that, we got certain noise. So, and that became our data. Our goal is really giving the vector B to reconstruct the image or the vector X. So all these relationships, again, can be written as a system of equations. And of course, when we try to solve that, or the corresponding least square problem, then we are going to enlarge these errors. And then the image that we obtain is useless, right? I mean, we started with this, trying to get here, and it got really worse. So how can we still, what math or what can we still do to solve this problem? Okay, so typical one standard method is to still use a variational approach where we impose extra conditions by adding an extra term. Those here the conditions will be problem dependent. But here I have an example that's related to our motivating example. Here this blue curve here, you can think about that was one of those steps in the beginning. And then the red one is what happened after it got blurred. Okay. Now, if we use Q equal 2, this is the standard Tikhonov solution, and here I'm using L, the discretization of the first derivative operator. So basically, in some sense, I'm imposing that the function needs to be smooth. Okay, and this is the solution that we obtained. You can see it's okay, but we are not that happy. And in particular, in this application that I mentioned at the beginning, the images are very high resolution. These are very large images, and what they really care about is the details. So this signal that we see here is really bad. Okay, this is like basically like useless for this application. So we really need to improve in the method to reconstruct images. So here there is another example or another reconstruction where Q is 0.1, as was mentioned before. That means that now this is going to be non-convex. Well, no, yeah, so I mean, everything gets much, much complicated. Here, actually, still I use the standard method, which is the iterative reweighted least square, similar to what Mirieta mentioned before. Basically, you can modify this norm, replace it by something that contains the 2 norm, but with some extra weight, because you really want to still approximate this expression that you have. All right, so I hope I made the point that we really need to use other norms here than the 2 norm. Okay, now let me go back for a second. Here, when I'm showing you this, I am assuming that we know exactly who is this matrix A. In reality, we don't know, okay? So it might be estimated, or we might have an idea, or, you know, maybe the engineers try to model and know, yes, you know, the blur looks like certain form. So for example, here, I'm going to assume that, for example, the way that this is deformed follows certain functions. So here I have an exponential function. Here I have something that is another bump. Okay, so here I'm going to assume that we have certain idea of what is this blur, although we don't know it exactly, but we are going to parameterize it, right? Because we are going to assume that it has this form. We can think about this as kind of curve fitting in some sense, although not the way we will write it, but in some sense we are going to do that. Curve fit, in some sense, our blur. Okay, so we are going to assume that it has certain form, and we need to find certain parameters. Okay, this is really the the kernel in the convolution or the 1D point spread function. So we are going to assume that the matrix A can be parameterized because whatever we put in the matrix A will depend on this function, and this function depends on the parameters. Okay, so now what we want to minimize is basically what we had before, except that we don't really know A exactly. Okay, the only thing that we are going to assume it can be parameterized by a vector of very small size. Okay, and that is important because if y was very large, then this might still be ill-posed for the y, and we might need the regularization term for the y. But here we are going to assume that y is like this case, maybe 4 parameters, so we don't really need regularization for y. One more comment. Notice that still this is a linear in the sense that A is a matrix times X. So the model is still linear, but now our unknown is also Y. So this becomes a non-linear problem because of this term. Okay, so it's going to be harder to solve. And the techniques are going to be different. So for instance, in general, when we have a function here nonlinear, but we have the 2 norm of that, how do we solve a problem like that? Well, so one approach is to use Gauss-Newton method. Basically, it's an iterative method where really the idea here is to linearize. Right, so we have a function, a nonlinear function. We are going to linearize using Taylor, basically. So we put that there. In general, we have the f first, and then the j, right? The function plus the derivative. Here I changed the order. It doesn't really matter. And we are going to iterate. Okay, so we are going from needing to solve a nonlinear least square problem to solving a sequence of linear problems. Okay, because this is the Jacobian evaluated at the point, so this is going to be a matrix. Okay, S is going to be an unknown, a vector that basically corrects our current solution. And then our right-hand side, this is a vector, okay? All right, so this is a standard method to solve this kind of problem. So coming back to our problem, and notice here that I forgot just for a second about the regularization term, and that is on purpose. It will come back, but just to see how it fits in the Gauss-Newton method. So before we have the general case where we have f of m. So this method can be applied. F of m is going to be all this that is inside the 2 norm. And then our unknown vector of unknowns will contain x and y. Okay, so basically we can apply Gauss-Newton, a very standard method for this problem. And this is how the Jacobian will look like. And I put it here because I want to emphasize something that we need to know for later. And that is that here in the Jacobian, we need actually, somehow we need the vector x. Okay, notice that here when we iterate, okay, this M contains X and Y. Okay, so we are iterating. There will be some X of Xi and Yi. And when we compute the Jacobian at iteration I, actually here we need Xi and Yi. We are going to evaluate them there. Okay, so a few more things. I'm using actually the expression that these mixed kernels, or the expression for the kernel that I gave as an example, and I'm writing things here just to show you that basically when we need to compute the Jacobian, somehow the only thing that we really need is to compute the derivative of our PSF function, okay? And that will construct a matrix, our matrix. And then we need the vector X, okay? Just keep that in mind. That's the only thing I want you to really remember from this slide. All right, so in 1973, Golub and Pereira came up with what is called the variable projection method to solve this very special problem. They noticed that if you look at, well, it wasn't actually exactly this problem. They were looking at other problems, but basically it can be applied to this problem. And they noticed that, this, if y is fixed for x, this is still a linear problem. Yes, it is nonlinear for y, but for x is linear. And they said, well, we should take advantage of that because linear problems are much easier. So in particular, or moreover, the solution for y fixed, the solution of this has a closed form, right? So the solution of this problem for y fixed is just this, okay? So you can, I mean, for y fixed, you can state the normal equation and say who is x. And because x has a closed form, you can plug in, replace x by this expression, and then your whole function, your functional now can be written only in terms of y, okay? So by doing that, now you can, if you want, apply Gauss-Newton to this, right? It's exactly as it fits that in the sense that we have here a function, a nonlinear function, and now we minimize with respect to y. And they say how the Jacobian will look like. And another thing that I want to mention here is that in principle, we are removing the variable x. So we shouldn't worry about until we actually really want it, right? So what I mean is here we have a problem that only depends on y. We could apply Gauss-Newton, iterate, take values of, when we iterate, we will get updates of y, but what happened with x? We could at each iteration compute x, but if we don't really need it, we could go until the end and then obtain who is x. But here, for example, if you notice or as I mentioned before, in the Jacobian, you actually can write the terms here. If you have the A pseudo inverse times B, that is actually x. So if you have a easy way to compute x, when you have to compute the Jacobian, you should use it, okay? So in summary, it is actually good to compute the x, actually to use it to compute the Jacobian. Okay, so this is in the PhD thesis of Julian Chang that several of you know, and Jimnei was her advisor. Her PhD thesis consisted of developing algorithms to solve this problem for y fixed very fast using a Krylov method. It's a hybrid method, basically a Krylov method with regularization. So she developed a method to solve this very fast. Notice that here our regularization is back. Actually, I tried to put it here so it is obvious. So here, yes, I put the regularization back that you can rewrite this way and then have in some sense a larger least square problem, right? You could rename this as our A tilde, and then we are back to having just this AX minus B. Okay, but really the part of her thesis, Julian's thesis, was also that not just to solve this fast, but actually she looked at the separable case, and inside here, when when using the variable projection method to compute the X that will go to the Jacobian, she solved it in a very fast way, okay? By the way, I haven't mentioned, but when we are looking at this problem, we are thinking that our problems are very, very large. So we really need to solve everything super fast. By the way, notice, and let me go back for a second, but our Y actually is very small. So we don't really need to worry about this step, okay? This problem is going to be very small, okay? But computing the Jacobian is a mess, okay? So, all right, so as I mentioned at the beginning, we really would like to here to put more complicated things. Okay, so we'll start by putting the regularization that is the 2 norm of Lx. Okay, so Julian's work has L equal the identity. So first step to generalize that work a little bit is to change the identity matrix by some other matrix here. And we can do the same as before, right? I mean, nothing really surprising here. I don't know which word to use, but basically the minute that we change or use the 2 norm, again, we can stack everything in a 2 norm and we can use the standard Gauss-Newton. So no assuming any separability. This problem is just one nonlinear least square, and we can use Gauss-Newton. All right, so, but let's use separability because it has been shown that it's way faster than just applying Gauss-Newton to that problem. So, yes, so here we can just use the variable projection method, okay? The difference is that now here, when we want to compute X, well, we might use fast solvers for this problem, different from the original paper by Golub and Pereira, different from Julian's approach, because this L now, it makes a difference, okay? So, but we can use fast solvers here, use this X to actually compute the Jacobian that we'll need it, and then apply, solve this least square problem and update, right? So again, it's just in case if this is to be clear, in this iteration, we are computing Y, but so we compute the Y, we update the Y, then we, with that Y fix, we can solve, this is going to be known, we can compute this, get an X, compute the Jacobian with that X, put it here, solve this regularization, this least square problem, update Y, and repeat. Okay. Now, we really want to have the Q, something different from the 2 norm. So for just a second, I will go back to where we actually know A. Okay, so how do we solve this? I mentioned the iterative reweighting least square method. But if A or this problem is very large, then an approach like the one Mirieta mentioned before is very helpful. And the idea, again, let me repeat, is instead of having that Q, oops, you don't know this, but my computer starts like losing energy. We have to hurry up. So the main thing here is to replace the Q norm by a 2 norm, but it still needs to be a good approximation, right? But here actually we are doing this majorization minimization approach where this P or this weighting matrix here has a certain form. All right. So if we go back to the nonlinear case where we don't know this matrix A, Well, we really follow the same process as we did when we had the 2 norm here. But when we have to compute this x, we do have this q there. Okay, so basically here, the main difference here will be that here for x, we will use this measurization MMGKS that Marietta mentioned before to make this, to solve this very, very fast. And then compute, plug in. So here I'm reformulating what is this problem where it doesn't depend on x, but basically use that x that we get there to find this Jacobian and solve. So there's no, hopefully it is clear what are really the changes from one problem to the other, but things that really need to be incorporated. Okay. I'm going very fast, I think, so I can, no, I'm not going to very fast. I started 10 before, okay. All right, so I'm doing very well, actually. All right, so here an example, numerical examples. Here I consider a PSF that really is a Gaussian, so you can think about a mountain surrounding the pixel. Here we have 3 parameters. This sigma 1, sigma 2, and the rho. Okay. And we are going to use different regularization terms. So the identity, because we want to compare, here we have something that basically has different directions, the x and y different directions, second derivatives. Here, this is framelet. You can think about wavelets if you want, something that is going to enforce edges. Okay, and okay, so this is what is the real image that we actually want to reconstruct. This is the PSF, the point spread function that actually we want to reconstruct, right? This is the representative of our A matrix that we really want to have, or recover, that in reality we don't have. We are modeling with these parameters, but we don't have. And this is data, okay? And to get this, we took this function, we blur it with this and add some noise. And here we have some results already, and we can see that we have to give initial guesses to start this whole process. So we gave some initial guesses for the parameters in the blurring operator, and then we see that they are converging to the real values, which are 3, 4, and 0.5. Okay, so that's good. More pictures to show that, yes, so we start and it starts iterating, the method starts iterating and the image improves. And the same with the blur, okay? Another example, this is what we consider the true image. This is, again, an exponential function, a Gaussian blur, and then this is our data. So given this, we want to get here. Of course, we'll never get here, but we try to get as close as we can. So some examples here to show that we are improving. Actually, I don't remember exactly what, maybe Marietta remembers, what are these 2 columns. I don't remember if these are different.
The first one are without using our solver, like just by using the Gauss Newton, and then the other one is by our solver.
Yes, perfect. Yes, so this is because here we are still testing when we have the 2 norm and when we have another norm. So, and here are the corresponding convergence curves. So this one is for the 2 norm, and here we play with other Q norms. And you can see this is for the X, so how our solution is getting close to the true solution, and here in terms of the parameters. All right, just on time. conclusions. So we introduced this variable projection method for general matrices L, any norm P, expression from the Jacobian that I talked a little bit, but there are more information in the paper. All right, and I'll stop it there. Questions?
Oh, thank you very much, Malena. Questions or comments?
I can ask a strange question. So why did it take the last 10 years to get to this point from Julian's thesis to this improvement?
Well, now we are using some of Mirieta's results, right? So the part of how you solve the P norms of these P norms using Krylov faster, those are more or less newer results. I don't know if that justifies it.
And Julian Chang already was using Golub Pereira results?
Yes. Yes, it's a very popular method.
You know Pereira is Argentina.
I didn't know that Pereira is Argentina, but what I found is that, actually we have to move to the next talk, but Hugo Skolnick worked on this area.
Uh-huh.
And
yes.
in one of these papers, he thanks, I think Golub thanks Skolnick because he was visiting him in Chile.
Okay.
Or in the Balseiro. Yeah. Anyway, we should keep going.
Well, and we are ready for the last talk of today, and actually the last talk of the session that will be given by Lucas Bali. And the title of the talk is A New Method for Reading Passive Microwave Data with Mixed Measurements and Spatial Correlation. Hello, Lucas, how are you? Thank you.
Hello, thank you very much for the presentation, for the introduction. I will now allow me some time to adjust my Zoom settings. Wait, share screen. Okay, and now just going to set this on full screen. Okay, can everyone see?
Yes.
Thank you very much. Well, this is a joint work between myself, Manuela Cerdeiro, Mariela Reifberg, and Rafael Grimson. We are essentially, we are going to do an application of inverse methods or image reconstruction to the problem of passive microwave remote sensing. So first, we are going to do a little introduction regarding this technique, this satellite technique that is mostly used to obtain and measure radiation emitted from the Earth's surface and essentially capture information regarding different properties, geophysical properties of the land. For example, soil moisture, land surface temperature, determination of floodings, and vegetation structure. This is quite used for the classification, eventual classification of different types of vegetation types. Essentially, that's the principal idea is you have here a sensor, a passive microwave sensor, which captures information coming from diffuse radiation from the atmosphere, radiation coming from the Earth, radiation coming from reflection of the sun and an object, and direct radiation coming from the object itself. So there are kind of like 4 sources of radiation that is captured by the passive microwave. One advantage of the passive microwave, and instead of using active SAR image processing, is that it's quite cheap. You can obtain measurements in a high frequency way because you don't have to send a signal from the satellite. You just need a receptor mechanism to capture that information coming from the Earth. So you will have a lot of amount of data available in a high frequency way. This is a characteristic of microwave. It's useful in day and at night, which is not something that is a problem with optical images. Can penetrate through cloud cover. The bandwidth of the microwave signal can penetrate, well, essentially between, through clouds. But there are some problems. For example, one of them is that they have low spatial resolution. Imagine one measurement, it's like an ellipse covering tens of kilometers of area from the land. And there is overlap in the different measurements. I will show you an image right now. For example, this is an X-band example of a recollection of an image and measurements coming from a passive microwave. As you can see, this is the province of Buenos Aires. This is the city of Buenos Aires over here. And each ellipse is a measurement. As you can see, it almost covered the entire city. And there is a lot of overlapping between different ellipses. So this is a problem, and this is something that needs to be handled so as to obtain a finer measurement for each, for an arbitrary discretization of the land. Another thing that is important to say is that there is a differentiation between measurements coming from land and measurements coming from sea. And this is something that we are going to talk about in this presentation of how we manage to solve these border effects that can be between two different regions. This is another example with K-band example, which is a finer granularity. There is still some overlap between different measurements. And now a little bit of an introduction regarding the mathematics of the PMW model, the passive microwave model. Essentially, we have an equation that is the antenna brightness temperature, TA, which is an integration over the Earth's surface between a geometric factor G. This is the projection of the satellite onto the Earth, the brightness temperature of the proper Earth, of the proper land, a differentiation, an area differential, and an epsilon, which is a noise term, an observational noise term error. This is an example of, well, a handmade example. As you can see, this is the province of Buenos Aires, Bahia of San Borondón. This is a different cells, different land cells. And these are different sea cells. And this is one measurement that captures information coming from lots of land cells and some sea cells. And well, the geometric factor would say that this cell contributes quite a lot to the antenna measurement. This contributes also quite a lot. This one contributes very little, since there is very little overlap between this cell and the ellipse. The main objective is, when you discretize your region of interest, is to obtain the brightness temperature for each cell. Consider you have a lot of these ellipses going around throughout the region of interest, and you have to reconstruct the original brightness temperature of the land, or the sea, I mean from the discretization of each cell. So the mathematics for the discretization is like this. You have Y, which represents antenna measurement, X, which represents each measurement coming from each homogeneous cell. We assume that each cell has the same brightness temperature. K is essentially coming from the geometric factor. It's an integration in the cell of the geometric factor, which is assumed to be known. This is a kernel, which is assumed to be known. And epsilon is the error term. In a kind of way is like what Malena talked about in the previous presentation regarding image reconstructions. There's some difference. For example, the kernel is assumed to be known, is a computation, a geometric computation coming from the Earth and doing some spherical trigonometrics. So this simplifies a little bit the problem. Well, this problem usually is overdetermined and it has no exact solution. So we'll provide now different gridding methods that allows you to reconstruct the brightness temperature. The most simple one is the least squares. Essentially is minimize the square difference between Kx and I. Very simple to implement, very canonical, very but it does not take into, it has some problems. One of them is very non-robust. Is very. I will show you an example, and it does not consider spatial correlation between neighboring cells, which is something we are going to talk about in this presentation. And it doesn't also take into account different kind of land types. For example, a land or earth type and a sea type. This is one example. This is a true brightness temperature, and this is the recollection obtained from the least square, which is not very good at all, very messy, quite chaotic. So, well, we have to improve this in a way. This is a more complex method. This is what we call an expectation maximization method. First, you have k different type of cell types. Just suppose that there is land and sea, to simplify the exposition. Assume that each cell type has a normal distribution with the parameters depending on the cell type. For example, if it's land or sea, it will have different mu and variance. The observational error is coming from a normal distribution where you have to know the observational error, the sigma square. If you don't know it, you can handle, but it will get harder. So the parameters are all the different mu's for each kind of cell type. For example, 2 mu's if you have land and sea, and 2 sigmas if you have land and sea. And you can have a closed expression for the mode of this conditional distribution. That means the cell brightness temperature, the antenna brightness temperature, and the parameters. If you know the real values of the parameters, you can get, using Bayes' theorem, essentially you can get an expression for P, obtain the mode, and have this solution, which is essentially quite typical from inverse problems, discrete inverse problems. Essentially, Sx will mean the covariance matrix of the cell type, which is, if you know theta, is everything here will be known. But theta is usually unknown. So you have to estimate it using expectation maximization procedure, which I'm not going to talk a lot about this since it's not a special point of interest in this presentation. But it's actually quite good. It can handle different cell types, and it is something is kind more robust than the least squares method. It shows good results. But you have to know sigma ops, the observational error of the noise term. You have to eventually, if this is unknown, you can estimate it using an expensive cross-validation procedure. Then, this is an example for reconstruction. As you can see, the expectation maximization method shows a much more improved reconstruction of the original image. It's not very noisy, shows the spatial correlation as was originally in the original image. It can differentiate better between land and sea. And then our last method, which is the one that we are essentially proposing, is essentially a Tychonoff regularization. As you saw in the last previous presentation, essentially you add to the least squares error a term that it regards a regularization penalization operator, calibrated using a lambda. We will talk about this calibration later. But essentially, the regularization operator penalizes cells that are neighbors to the original cells and are of the same type. For example, if you have land, it takes all the land cells that are surrounding this cell and it penalizes if there is a difference measurement between the center, the original cell and a neighboring cell of the same type. If, for example, this cell over here has all lands neighbors, so we will penalize it if there is a strike difference between this cell and this one. But here on the frontier between land and sea, it will only take into account, if this is a land type cell, it will only take into account land cells. So this penalization operator is somewhat, it handles spatial correlation, but considering the same type of cell types, if it's land or if it is sea, for example. It has a closer solution. If lambda is known, you have a closer solution with this expression. This can be found in the book, in this book of Clive Rogers, remote sounding. If you don't know lambda, we propose over here a leave one out cross-validation procedure. You essentially just do this a lot of time for each value of lambda, remove one of the antenna measurement, obtain the least square error excluding that antenna measurement. This is the typical, the typical characteristic of one cross-validation procedure. And obtain a closest solution for XY. With this XY will be the brightness temperature for the cell type in a situation where the antenna measurement I is absent from the retrieval. And then you just essentially try to minimize this expression, this leave one out cross-validation expression, between a grid of values for lambda and choose the best lambda. What's the problem with this method? It is expensive. As every kind of leave one out cross validation has a heavy computational burden, it needs a lot of computation, one inversion, not only for each lambda, but also for each antenna measurement. So imagine this can be very hard to, it's easy to implement, but needs a lot of computational power. What we found is after in a book regarding inverse discrete method, proposed a generalized cross-validation procedure for this kind of problems. Essentially, I'm not going to get myself into the dirty details, perhaps, of the procedure, but it's quite easy to implement. It only requires for each lambda one inversion. We obtain this kind of pseudo inverse of K, which is like an adjusted kernel. Obtain the retrieval for this K, and essentially compute the error of the total error for lambda with this expression here, which only includes a norm 2 operator and a trace from a matrix. The most expensive operation here is essentially an inversion, but it's only one inversion per lambda, as I say here. This is the result. It's quite similar to the expectation maximization result. Fortunately, the advantage is that it's much cheaper and it does not need a special calibration as happened with the expectation maximization method, where you had to know the observational error. Not the observational error, the variance of the observational error. some scenarios where we try this method, synthetic scenarios over here. This is a purely random scenario with different random mechanisms for land and sea. A purely here over in the right, a purely spatial correlated scenario, a trigonometric function applied over the land and a different trigonometric function applied over the sea. This corresponds to alpha equals 1. This totally random equals correspond to alpha equals 0. And this is a compromise, alpha equals 1/2, which is a convex combination, depending on alpha, between the purely random and the purely trigonometric scenario. So as you can see, with different alpha, we tried the three methods. Least square always behaves quite bad in the root mean square error, just doesn't get better with the alpha, does not take into account spatial correlation, which is a bad thing for the method. Expectation maximization does take into account, but it tends to not get up to a point, as we can say, depending on the band. After a certain point, the Tikhonov proves to be much more performant than the expectation maximization, because it's, how can we say this? In the expression itself, in the regularization operator, the penalization is included, specifically taking into account neighboring cells of the same type. This is a real situation, a real scenario where we try this. This is a polarization index. This is not brightness temperature, but it's something similar. It's a combination between different polarization coming from antenna satellite measurement that using for different bands allow us to reconstruct this kind of patch over here in the province that did correspond to a flooded area situation in that moment. This is what actually quite a concrete flooding happening in the center of the province of Buenos Aires. Well, and so to conclude, in general, as the Tikhonov method is essentially as effective or even more effective than the previous methods, expectation maximization, but with no calibration needed because it has a very fast cross-validation procedure. Does not need calibration for the observational error. Both methods clearly surpass least square, which is very basic, which it also surpasses other methods. We tried Backus-Hilbert, which is used for geophysical inversion problems. It's very expensive to run, and it did not prove to be very to give good retrievals. And we recommend the this kind of Tikhonov adaptation method for especially highly correlated scenarios. A little bibliography, some papers. I especially recommend, I'm sure everyone here on this room know this book from Roger, The Inverse Method for Atmospheric Sound, a beautiful book. Well, we use a lot from Astor, I didn't put the year, sorry. Parameter estimation inverse problems, which give us the motivation for this kind of fast cross-validation procedure. And well, essentially, I think that's pretty much everything. I don't know in time, but essentially that's my presentation. If you have any questions.
We are in time.
Thank you very much.
Thank you, Lucas. Thank you very much.
Thank you to you.
Any questions or comments?
Yes, if you have any questions. I don't know how to stop sharing. Oh, here. Over here, there.
And we have also now sometimes that was planned to be like a networking if there's questions or comments on the work of Lucas, but also if you want to say something or I don't know. Or to introduce yourself, there are some